I wanted to get to doing friction as a core concept 5, but before that, this morning someone asked me an interesting question as I was walking back from the gym, and the question he asked me was about something he'd learned when he was in high school many years ago, and he really said, "Oh, I learned some formulae about force and the equivalence of force and energy," and I just occurred to me that there are a lot of what I call special case formulae. Just as in the previous video I addressed a formula of convenience that I wrote down here, I figured let me use this video to go over a few formulae, kind of show you how they're arrived, explain why they're special cases, and then also maybe explain to you how in several curricula across the world they're taught to students without the intuition of the special case, and then you get problems stated as well. So I'll try and address some of them, and while I do that, I also want to go back to this problem which I had, and I think I talked about it in the basic concepts. I talked about it in core concepts 1 about the chalk that fell 1.2 meters. And during that, and I'll start with this here first, right? And during that time, I think I had told you, really the impact was much higher when the chalk was coming down this way, and it broke, it shattered into 3 pieces, and I kind of told you, well, there's a very rapid change in momentum, and we had, mass times velocity. We computed final velocity is about 4.9 meters square at S is equal 1.2 meters and A being equal to acceleration due to gravity. And I mentioned to you this final velocity gets very, very rapid. This velocity and this momentum gets very rapidly taken out to 0. And I mentioned a very tiny, tiny instant of time, and therefore the force was really heavy. Now, and remember that, and I'm going to try and help clarify that as well, because that's an interesting question about that time, and therefore what is the force and what happened. And now that you've studied some aspects of energy, hopefully it'll be clear, right? So I'll address all of that, but very, very just as I get started, one of the things here, we know the S is equal to ut plus half at squared. Hopefully you can intuit that now. We also developed this formula of convenience really by multiplying S and A, and then we played with the U plus V and the V minus U, etc. And we got some formula, but I wanted to just address a special case for you. If you were falling, if it was free fall with initial velocity 0, you could position this initial velocity to be 0, in which case velocity squared would be 2 times acceleration due to gravity times the height of the fall. People would give it as h, but just to be consistent, we use s for displacement. That is what you would get, which means velocity would be the square root. Okay, and again, pay attention. In free fall, velocity, and that's why I don't have a plus or minus, because there is no 2 directions in free fall. Free fall is a single direction. So you'll find this as what I call it a formula of convenience, right? But you will find this as a special case formula. Remember, be very careful if you just take velocity to be equal to square root of 2 times acceleration times distance. We got this as a special case when initial velocity was 0 and acceleration due to gravity, right? If it was straight line motion with no other factors, then you could write this as well. So this is another formula that gets explained to people, but this is a special case of when U is 0. And if you have this case, remember, you could technically have a positive or a negative sign here, because velocity is a vector, and if it's a straight line, it's not free fall, you don't know left or right, you could technically do plus or minus, and depending on the direction of the acceleration, you would effectively have. So this is a magnitude calculation, really. This is a magnitude calculation, right? Remember that when you see this formula. So again, what's one of the formulas of convenience? I will just put that here. Root 2 AS And remember this to be typically just magnitude, something I have not seen a lot of textbooks talk about, but conceptually I hope you remember that. Let's just play with this a little bit more and see if we can do a few other creative things. Let's keep that there. Let's come to our force equation. This is another part where I see some creative things happening. Remember, we told you that work is the kinetic energy final minus kinetic energy initial. If initial velocity was 0, technically, and we only had final velocity, you could effectively have written this work as just 1/2 mass times velocity squared. I have seen problems where this becomes a question, and you're given a velocity value, and they expect you to, and maybe the way to write it is I'll write force times displacement. So you're given a velocity value and a mass and a distance, and asked to find force. Remember, this is a special case for when u is 0, but sometimes problems will only state this. So understand this. It's not as simple as just saying, some people just say force times distance equal to energy. And I've seen textbooks say this too. This energy is the difference of the energy. Remember, here we had a factor of 1/2 mass times an initial velocity. We assumed the initial velocity squared, actually. We assumed that u to be 0 to get this formula, right? To get this formula. So it's really the difference. It's energy that's being imparted into that object by this force acting through this distance or this displacement. So remember that, because sometimes I will see formulae which go like force is equal to energy divided by displacement or distance. Again, I'm using displacement here because that is the correct vector to use. Remember, velocity is displacement over time, so I'm just keeping, you might find that as distance as well. So some of these are what I call special case formulae, but questions, they get taught at a much younger grade, and students memorize this formula, but I want to make sure you understand the intuition here, right? So that's, I will see these kind of, F is F, and I'll see this. So this is a very common, I've seen questions being asked in 9th grade, sometimes 8th grade students, which is, and sometimes they call it D, and they might just write this as E by D, where D is the distance. But again, these are all just special case formulae that get included just to make you solve problems, and I want to make sure the intuition is understood. Special case derived when initial velocity was 0, or otherwise this is really the delta energy of that object. It had mechanical energy, and then after the application of the force over a distance, its energy changed. This is really that delta energy. There are some problems where they will give you that, hey, an additional 160 joules was imparted over 3 meters, what might be the force? Then yes, this makes perfect sense because it's already delta energy. Okay, so just remember that part here. I have seen other creativity going on here, and let's see what else we can do. We have some problems here, and we have some problems here. So if I'll go back. For the time being, I'll just take this out and just go back to this formula, and I can show you velocity squared is nothing but 2 times a acceleration, as again in a special case where u is 0, right? Assuming if u equal to 0, velocity squared is equal to just 2 times acceleration times displacement. You can play with these equations because I can now write this as force times displacement is equal to, remember what happens here, I'm going to substitute the velocity square, so I'm just going to have something that would look like mass times what happens here. The 2 and the 2 cancel out, and then you're left with A times S. Intuitively, it makes perfect sense, because if S goes away, force is equal to mass times acceleration, right? So remember that. At times, you may also flip this around and say, if I've seen all kinds of variants of this being stated, if I write this in terms of velocity, I could write this as equal to just look at what I'm doing. It really just seems like me doing creativity, right? So I have all this variance. I can remove S, and then I can write velocity is equal to, if I bring velocity out, it's just force times time divided by mass. I mean, all these are just playing with these formulae. Come up, you can move them around in so many different ways. But I just wanted you to understand that a lot of the formulae you'll see, you wouldn't have to memorize them if you knew what was happening fundamentally, right? So if you were given velocity in a problem, and the problem didn't state anything else but just said energy, you can conveniently use this formula, because that's the only possible explanation to this, right? So remember that. Let me just see if there's any other interesting derivative that we can build out here, right? What else might we write? We could write. I'm wondering if I can play with this and see if I wrote force times displacement is nothing but velocity times time is equal to 1/2 mass times velocity squared. If that velocity went and the square went, yeah, it would come back to that same. I think I could write this equation. It's probably the correct way to do this. Is I could write. I could do either time calculation by saying time was nothing but 1/2 mass times velocity divided by force, or I could write velocity was nothing but 2 times force and time divided by mass. Still just playing around with things here. Yeah. So some of these things to remember. You get asked questions that typically will give you distance and ask you to find distance and give you energy. Sometimes they'll give you velocity and ask you to find force. So there's all of these different combinations, right? If you have an object of mass m that travels, let's say, at a velocity v, an object of mass m traveling at a velocity v for a time of 5 seconds would be equivalent to what is called as an impact force of F. So again, this is special case, right? Because in order to get here, we set u to be 0. If u was, say, 10 meters and final velocity was 40 meters, then really this v is the 30 meters per second. U was 10 meters per second, v was 40 meters per second, then really this v is the 30 meters per second. That's the additional change of kinetic energy, which means there was a force in play. Otherwise, there wouldn't be a force in play, right? There was a change in kinetic energy. So remember, again, special case. So object, but the problem will. I've seen a lot of problems with object traveling at a velocity of 30 meters per second. For 3 seconds, what's the impact force? Well, the assumption is the increase in its velocity was 30 meters per second. It was traveling for time of, say, 3 seconds, and its mass is 1 kg, and then you could just say, well, it generates an impact force, which is the force of impact of that, that's how it's measured, and that's really where they're going with it. Again, it's a special case, because in theory, you see here, you don't know this tiny instant of time when it collapsed, so you have really no way of determining that force, right? So impact force this is more of a horizontal movement where this impact force is calculated. Don't try to apply that here, because you wouldn't be able to calculate that impact force. You could technically, because you would argue that the object was falling and there was more time, but I would argue again to you that, sorry, with acceleration due to gravity, as time passes, velocity kept increasing. So at any point, you couldn't say, oh, it came down here after a time of, say, let's say 0.5 seconds, it got here, but that was at this velocity. No, the velocity actually changed. So don't try to apply this to get this, right? So I just wanted these special case formulae out of the way. Now I'll just address this, what exactly is happening here. I kind of told you it's very tiny, you wouldn't be able to find out the force, but we did calculate yesterday, or in the previous video, that there was kinetic energy here resulting from this fall. I'm going to use green for my kinetic energy, and we used that formula by substituting into half mv squared because initial velocity was 0. Kinetic energy was the mass times square of velocity, which we know the square of the velocity in terms of free fall is 2gh. So we came up with this, that half and the 2 cancel out, and it was really m times this times s, which if you think about it was equal to the work that I did in lifting this object up here, right? So we came up with kinetic energy. So we had kinetic energy, we came down here, and what happened? The chalk broke, right? Momentum reduced, but the chalk broke. We really can't calculate that exact force, but what I want to leave you with is this idea of what happened, right? This kinetic energy, this is potential energy 0, and we know conservation of mechanical energy. You couldn't just say, oh, I'm just going to come down to rest here at this kinetic energy. Well, no, as soon as you're at rest, kinetic energy is 0. This is already P is 0, so what happened to that total mechanical energy? So that change in momentum that went from mass times 4.9 meters per second, that initial momentum got changed to a mass times 0 because you came to rest. That change in momentum has a contribution from this energy. This energy gets lost. You go from mgs to 0. That's one part of what happens. So there's one contribution there. That still doesn't explain a lot of things. Now, if it was a soft surface, you would see on a soft surface, if this was just soft, and my chalk would land here, maybe I'd draw the chalk with white. It will compress this soft surface and it'll go down. It might be down here. And there you could say, well, I have distance. I have some distance that you traveled where this kinetic energy effectively went down, and then you kind of reduced that energy. That energy resulted in something. As that energy changed, change of energy translated to work. I could say, and I know work is force times distance, I know this distance, I could talk about what that impact force was. You can work that out, right? Because mgs is becoming 0, kinetic energy comes to rest. mgs would be equal to work done. Work done is force times this tiny distance here. If I call this distance d, then mgs is equal to force times this distance d. I could calculate the force. And naturally you could say that equation would become something like force is equal to mgs, which is the height of free fall, and this d is sort of the depth into which this object falls. And as the height goes up, you can imagine what would happen. Your impact would be much higher, but the depth, if it's a soft surface, it kind of shrinks in. But if this depth is very minimal or hardly anything, then would you say the force is infinite? Well, hard to say force is infinite. We cannot compute this force. What happens then to the energy? Yes, part of the energy goes to reduce this momentum. That takes out energy. Sometimes it comes out as heat, right? There is a possibility that another part, maybe there's heat generated at that point of fall. It's a possibility, but we won't get to heat. I will address another action that happened, and this is a good segue to our next section. This chalk broke when it had the impact, which means that energy translated to the particles of this chalk kind of shearing, they just kind of got displaced. There is an internal molecules of this object we're holding together, there is a natural sort of force that's resisting them from moving and becoming liquid, right? That's called internal friction. So when we get to friction, you'll see that internal friction is one of the types of friction, and really what happened is part of that kinetic energy got translated to a braking force, and that force was equal to or greater than the internal frictional force of these components. So part of that force went to breaking them, and that was because there was frictional force that worked against it, overcame the internal friction force, and the object sheared and broke. That's part of where this energy goes into, right? An exact calculation of that would probably be very difficult. You probably need a computer to go through that and some amount of tinkering out with some mathematical models, but I thought I'd give you an explanation. So some formulae of convenience, special case formulae, special cases, remember, but you'll see them in problems. I just wanted to go through this with you. Hopefully you have a better idea and kind of clarify this, because I don't want to leave you, in the dark with this idea, right? So understand that impact force at the point of impact of free fall cannot be calculated unless you're going down, right? Unless if there's depth, then you can calculate the impact force. Otherwise, you can't get the exact value of impact force. But you can understand from energy that part of the energy goes to maintaining the conservation of momentum, sort of, goes in there, and part of the energy goes to go back to green. Part of that energy goes to breaking the object, which is to breaking the object, right? Which is really equivalent to overcome some kind of force of friction. And this is internal friction. But hopefully a good segue, and we'll talk about friction, I promise, in the next video onwards, okay? So until then, good luck, play with some problems here, and I'll see you soon.